Last week I started a discussion if it would be possible to 3D print a Benchy in under 1 minute. In order to print fast, we need to solve three issues. One being cooling, the other extrusion, and the last one a fast motion system. I used my old CMM to set up a really unique drive system that would allow us to go really fast. This week's video is about building a proper hot end that can keep up with a motion system. Da 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 da.
Good morning, boys and girls. So it's a beautiful Monday morning, straight into building a freaking hot end for the CMM machine. Thank you so much for all the support you gave in the first video about the topic. I'm really happy about all the positive feedback, the positive vibes, the people that are coming to the Discord server. I get this camera on me and also record my screen so we can have a look at the CAD side of things, and then we're going to go downstairs and just machine it, I guess. So here we go. This is the Z-axis you've seen me assemble on the machine itself. So I'm gonna make the hot end visible, but first of all, the main design criteria I had in mind is to, well, obviously get the filament heated up fast as possible and efficient as possible. So the problem with the current state of hot ends is you're gonna make your melt zone longer and longer to give the filament in its very short travel time through the hot end. The heat transfer isn't going fast enough. But if you extend your hot end longer and longer, you're gonna lose all your control about what's coming out on the nozzle tip. Because then your puddle of molten plastic is getting bigger and bigger, and once you retract a filament, it will have no real effect. So the main thing I'm focusing on is to get rid of that problem while still being according to the speedboat rules. One hot end, 0.5 millimeter nozzle. Back pressure of that small orifice will limit what we can push out of there, essentially. But in order to heat the material up in a very short and then controlled way, we gotta increase surface area, and that is my main goal with this design. Kind of the big idea is I think they're called CHT nozzles with this intelligent geometry inside the nozzle, where you actually do split up your filament and then the surface area is increased and you can get the energy throughout the whole filament strain. What we're building is essentially one giant hot end with 4 filament strains that are going in to maximize surface area, and then we're going to combine all of that into one orifice at the bottom. So what you see up here is 2 NEMA 17 extruder motors. These are quite some old pusher assemblies I had from previous experiments on 3D printers lying here. So if that becomes the bottleneck at some point and we need dual gears or something, we'll upgrade that. But coming from this pusher assembly, we're gonna have some very short Bowden tubes that are going into our cold end. This is a industrial heater coming from mold industry. It's 32 mil in diameter and can push up to 150 watts at 230 volts. We're gonna hook that up as the main heating element, and I think this will be plenty enough, considering that we got a huge thermal mass going on here. So here comes the magic. We've got 4 heat breaks up here, which will be made from stainless steel. We can switch it to titanium later on, but we got to get some data and install some sensors to see what the actual temperature drift will be coming from the hot end to the cold end. And yeah, we can still upgrade later on, but in terms of designing and prototyping, we got to get fast results, see where we're at, and then work with the problems we got, but leave the things that worked from the first try. So coming down the path of the filament, this is the only thing I'm not quite happy with for right now. There will be a kind of sharp transition coming from this to this slope, but we'll see what the effect will be in terms of pushing force. You can see how these four filaments will merge into each other. Yeah, another design criteria is to have like all the there should be the least amount of volume possible for the filament to be in. We don't want giant puddles of plastic or molten filament because that's going to just decrease our accuracy and control over the whole system. But yeah, as you can see, we got 4 filament strains feeding into one nozzle, so we got quadruple the surface area to begin with, and like the heating zone here, the diagonal is somewhere in the neighborhood of 35 millimeters, so that's like shorter than a volcano heat block or yeah, different solutions for high flow hot ends. But essentially we have 4 times the heating length, and yeah, we'll see what the limits are of this setup, if we have to extend it or maybe just even shorten it. That would be really interesting if other people want to like use this design and have that on their Core XY or Cartesian printer or Delta or whatever, so we can maybe make it a lot lighter than what it is. So apparently I learned something new this morning. I was looking for the bronze I selected last week, and as it turns out, I always thought that bronze was a really good heat conductor because of the high copper content, which copper is one of the best heat conductors. But as it turns out, it's like a fifth of that, and thinking that it will turn more and more into a real prototype build, I'm just gonna go for aluminum, because my main goal is to heat it up as fast as possible. So heat transfer is a huge number for me, and this 6082 aluminum is double the heat transfer as the brass, and like 3 or 4-fold the heat transfer as the bronze. So I think I'm just gonna go with it. Also machine the nozzle out of aluminum, and just gonna see what happens and see what the bottleneck is. Apart from that, we have some stainless steel here, and yeah, we're just gonna go over to the lathe and start fiddling around. And I did the first operations on all these parts. It's like the orientation there will be in later on. So let's head over to the mill and get all these features milled in there. The first part is in the vise. As you can see, I put it into 2 V blocks to hold it there, and I already picked up the work coordinates. So we're gonna mill that to final length, then drill 5 holes in there to accept like the standoffs from the hot end.
So we're gonna use this indexing chuck. What's special about this, I can loosen this nut and tip it at an angle so we can have like the gauge block sitting under here. We're gonna flatten the top to bring it to size, mill some features in this orientation, and then we'll tip it over. It's set up under the required angle of 17.5 degrees, so we're gonna use a 3mm end mill to create a flat spot. Then we're gonna center drill it and then do the actual drilling. That actually took some time. So the first one did end up in the trash bin because I was apparently feeding the drill too hard and got stuck. I didn't even bother to trying to get it out of there. I don't know, just did the raw stock again, did all the pre-work again, wasn't too bad. Yeah, this time it did finish drilling. So I'm just gonna flip it down again, mill some pockets, and then it's time to check it out and see how they ended up on the other side. Alright, so for the next part, I'm gonna have to drill those to be like a tubing. As you can see in these drawings, it will accept 2mm in diameter hole for the filament path. So usually I would do that on the CNC lathe, but I got some job on there I don't want to mess with, so we're gonna use the other lathe and put on the collet chuck and just do it manually on there. First of all, we're gonna face them to length, and then I'm gonna set up the drill with a very fine feed. I can hook this tailstock up to the cross table and then feed it very fine into the workpiece. Yeah, you can totally see that this lathe is in its natural habitat with these kind of drill sizes and chuck sizes and workpieces. So usually there's these big ass chucks on there and usually do work in 200 to 400mm in diameter range. I guess it works. Alright, meet me at the bench here. So I think machining of the parts is done for now. I can't really show you, maybe you can see a reflection of light down there, but I have no idea how to film this part. I can't even have a look inside myself. Turned out pretty good. Actually, these holes intersect pretty darn good at that spot there. The first thing we're gonna do is actually extrude some material without having the nozzle tip on there. That way we may get rid of all the material that's left in there or just hanging on a thread. If we get that stuck in the nozzle, yeah, we can like disassemble everything. Very short for that diameter, and it's just about 0.75mm until it opens up for that 2mm hole. Yeah, we can have a quick assembly. It's not that easy through the camera, but these standoffs, of course, fit in here.
and filament will get pushed through here. This fits nicely on here, and then we can screw on the nozzle. So the lowest point to get a temperature reading of the heat break situation, what kind of temperatures we have here and how much cooling we have to add. Maybe we'll add some kind of a controller to manage a reasonable temperature up here. And also I drilled a hole that's going just up to about this point. It's 12 mil deep from the surface. So we're actually measuring the temperature just 1 millimeter apart from the puddle of molten plastic in here, so the intersecting point of the holes. So that way we can get the most accurate readings. In terms of the other features, I just grabbed the first things I could find. This is a set from Angle Grinder. I can have this here, and yeah, like screw it with these two tools. This is the heater. Like I said earlier on, it's 150 watts and it will fit snugly up here. Depending on what the temperature readings will be, I may manufacture some insulating parts from PTFE or ceramics or something to have that on top and also at the nozzle tip. But I think main priority is, do a basic test how this one works, what the readings are, what the temperatures are, and go on from there. If this looks promising but needs a bit more finesse, I'll buy some copper and make it out of like the best material you can get, apart from silver. That's too expensive for this kind of stuff, but yeah, we could do it out of copper, we could nickel plate it, we could whatever. There are many things to do. Also, we have to design some kind of a shroud that's fitting up here. And also we have to design the nozzle tip that is eventually going to cool our part. Okay, so I think the next thing I'm gonna do is get up to the machine again and hook everything up. I have to install a few SSRs to deal with mains supply. I have to wire in all these thermistors, get it actually hooked up in the Clipper software, etc. And yeah, then I have to respool some of that filament because I need 4 identical ones. Then we can have a first go at extruding plastic. Last thing before I'm gonna go upstairs is when I'm putting this together, I will apply a bit of anti-seize on these threads because this is like bead blasted aluminum on aluminum. I want to make sure that this won't bite me later on. So, see you upstairs. And before I install it, just gonna give you a quick heads up on the weight situation. I mean, in this setup, it doesn't matter. Initially, I wanted to do that out of a different material, but I guess this is the most lightweight this version could be. You could shave off a few grams here and there, but overall, this assembly is like 127 grams. If you would like replicate it, you would need a heater, another 120. Need some kind of a bracket with some of these fittings up there, and that adds another 40 gram, which is just shy of 300 grams for this setup. We can compare that once I got the flow results in, how much like bang for the gram you get essentially. And let's have a look at that. Yeah, so we went with the first extrusion without a nozzle, and we're gonna continue that just for setting everything up. As you can see in the clipper, I added the second thermistor, which is sitting up here in the cold end. So this is like the first position of the cold end, and I already have done some heat testing. Left side is hot end temperature, right side is cold end temperature, and as you can see, by increasing temperature by 25 degrees C, it will increase temperature by 3 to 4 degrees on the cold end side. But I have just made a simple adapter for shop air cooling, and with its current setting and flow rate, it is right where I want to be, because like I think at the end we're gonna have temperatures of around 250 to 280 degrees for actually printing. We're working with PLA. I got from Monica McWolf, I got this recommendation. This is the filament she's been using. And for comparison's sake, we're gonna use that. Like if we add another 50 degree here, we would add another 6 here. So we would come right at the glass transition temperature of PLA, 55 degrees, somewhere in that neighborhood. And really set it at a point that the PLA will be at its glass transition temperature when it comes down into the hot end, because as I said in the CAD model, there is a quite sharp transition, and when I'm feeding the material in by hand, I can feel that transition being really sharp. Once I go in here with a lighter and just give it a couple degrees, the bend will be, there is no resistance anymore. So we want to have that to decrease the friction inside the hot end as much as possible. So the cold end temperature is a important variable for us. I've let it cool down since the last test and took a break. What we're gonna do next is I have to set the extruder steps accordingly, because with these 4 wires feeding in, I have to set it to a quarter of what it actually is to end up with the right amount of filament being extruded at the bottom. Then I have to take this spool and re-spool it, and then we'll do some testing with the 2mm orifice. Let's see how much filament we can put through here. And then we'll add the nozzle tip and see how much back pressure we're generating and how low the output will be then. And see how near we are at the like 250 to 300 cubic millimeters a second mark we want to reach. I'd say if we like reach 150 to 200, that's a very positive sign, because there is a lot of improvement to be done. Just making this out of copper instead of aluminum would increase its heat transfer by 2x. And then there are a few other variables we can deal with. So all right, so excuse me for the crude filming that was going on in last half an hour. So I've made some very basic first tests about the hot end situation, and that kind of worked. So it was quite hard to film because I have to be like 3 or 4 meters away from the machine to get everything in one shot. And also I had to sit here and control the laptop and see that not everything is burning to the ground. So what I ended up with is a bunch of stuff. There's some more here down on the floor. Yeah, so it turns out the heating capability seems to be quite alright. A tray down there and was extruded in like a bit over 30 seconds. Let's make that 32 or something. And I got that stuff here. This scale is at 0. I put that up here. I managed to extrude just over 9 grams in, let's call it 9 grams in 30 seconds. That means 18 grams a minute. And that was only at 220 degrees. But also, of course, there is a 2 millimeter orifice right now. Once we go down to 0.5, there will be loads and loads more back pressure. There is no way we can do that. But a Benchy weighs 12 grams with these slicer settings, shy of 12 grams. So if we manage to do 12 grams a minute, that would be a sufficient setup. Go for a sub 1 minute. What I need to address, I found loads and loads of problems. Of course, this is the first time of a prototype in action. So I have to address the heat break situation. I have way more contact areas than on the standard Hotend because I have 4 times the filament path, and I also got this stainless steel screw going all the way to the top. And I was monitoring the temperatures. The heat creeps up in those tubings. Get some titanium in the mail. Problem is, I just kind of find it shipped from China. So I guess I have to do that on my own as well. I would have done it in the first place out of titanium, but yeah, I just used what I had on hands to get first iteration results in. So I think it would be a great idea to shave down those diameters to give it less area. I'm gonna do some kind of a insulator here. And yeah, change material. Apart from that, I have to address the cooling situation. So it works out, but I basically have to run everything on full blast to not have the heat creep up too much. And that is, I mean, for letting this machine run just a minute, that's fine. But having the compressor run at full blast basically just to cool that cold end is pretty much of a waste and annoying as well. I had to use headphones and do a voiceover while filming. So I have to find a solution for that. Next in line would probably be way more testing of that situation and yeah, improving. But I guess if I want to close this video up, I have to print something. Otherwise, you will kill me in the comments. This isn't a good idea, but we're gonna try some print. It will be very basic. If it doesn't work out in like first or second try, I'm gonna shut it down. You will understand why that is. And yeah, let me just prepare something here. Slice up a model. Get the air bearing back into place, tune down the motors, etc., etc. And I'm going to see, I have no idea how to, I have to home that Z-axis by hand, so on and so on. Let me see if we can print something today, and then we'll wrap this video up. Alright, there you have it. It's one of the most perfect first prints I've ever done. I mean, I'm almost serious on that. Yeah, first prints are usually a pain in the butt, and yeah, and I'm kind of happy that we've got so far. So this is a 20 mil calibration cube, and it made it more than half its way up, and it's looking pretty. Yeah, but also we are able to identify so many problems, and that is, yeah, that is to be expected. I mean, we're not building a Cartesian or whatever printer out of the box with standard components that have been tested for thousands of hours by the whole community, and all of the components from motion to extrusion from whatever are completely prototypes. They haven't been tested, or there is very little knowledge about it. I would be shocked if it would work in the first minute. That's where we're at, and we have to talk about a few other things. So in terms of the hot end, I have to address many things. As you can see here, there is plastic coming up from the heat zone. That means I have to address those guys. Those are getting too warm. I also, like, the first print was also done with just one of these pushers installed, because I couldn't get all of them to work at once. I had it before and it was quite a hassle. So I have to get out the thermal camera and have to do some investigations on that. The motion system itself behaved. Everything is like working together. So from now on we can do real testing, but main things we have to focus on is, of course, get the cooling situation sorted, because there is no filming there. It's absolutely annoying sitting here. I have to find another solution for that. So there are many things to do, and I will address those in later videos and just work on that. This video is becoming really long, maybe the longest I've ever uploaded to YouTube. I think it would be best to make a cut here, but I want to mention a few things. So the amount of comments, and especially positive ones, is overwhelming on the last video. I absolutely enjoy doing YouTube videos and projects that have that kind of feedback. As I said in the last video, I tried to post this weekend, so 1 week later than the original video. And there are so many comments, I have no idea how to answer all of them. That would make another 2-hour video, I guess. One thing I want to address, though, is what I was aware of, but didn't mention it in the first video. But you guys actually saw the twisting motion this makes. And yeah, this is known by me. I think in my setup, the belt tension is the thing that allows the air bearing to rotate. Because when this is stretched in a straight line, the slightest amount of rotation does need the very slightest amount of play in the cable. And getting the proper tension on the cables is one of the things I spent the most time with. And I tested a lot of spring rates, but also spring isn't the perfect system, because if you just see that one axis, it's transferring its energy from the spring from one side to the other when you're traveling in that direction. Just when the air bearing is in the middle, the potential energy of the springs is in the center, or is balanced out. If you go to this side, this spring will get elongated and have higher force, and that is taken down from this spring because it's contracted. So eventually the perfect setup with springs would be to have springs with constant force. So finding springs with constant force is a kind of a miracle in this arrangement of forces. You won't find that. So from the start on, I've been fighting to get the cable tension as high as possible. Few people commented, and I just started to realize when I read that that having like these two and these two cables hooked up to one point of the air bearing would make it way more stable. That makes sense. Yeah, I do have some other solutions in my mind. We're gonna discuss that on the Discord. Let's see how far we come with the next iteration of the motion system. I want to thank all the people that commented on the last video, and honestly, there were so many good ideas in there. Let's keep it at that as a community project. I really like that vibe a lot. I want to give everything away, everything I find on here. So many things I can't really go into detail right now because it would just be too long. Like basically the hot end and the table moving in opposite directions to effectively double the speed, etc. There's so many great ideas you can find in the comments, and they're just being developed by a community, and that's what it's all about. So let's continue that. I would be thrilled.